Good evening, good evening. Can somebody let me know in the chat if they can hear me? Now there's a bit of a delay on this, so anyone, if you could just type it in and toss it in there. Good. That's what I like to hear. All right. Welcome to what I think is going to be the last teaching lecture of this year. 2020 for the semester. Next week, for a reminder for everybody, we are planning a meeting. It's just going to be some fun problems and more of a casual hangout, I believe. There we are. More of a casual hangout next week. Feel free to join us for that to cap off the semester. Otherwise, we'll get started. The contest for this week is set to start at 6:30. It should be set up. Someone will toss the link for that into the Discord for people, but it's already listed in contests on Caddis. If you look for the upcoming contests, should be the first one, set to start at 6:30. So with that, I'm going to disappear. There we go. And we'll get started with the Minimax algorithm and alpha-beta pruning. So first off, to start out, what is Minimax? So Minimax is a decision rule algorithm. It's important to know that it uses recursion. And what it does is it evaluates game outcomes for n-player games. So this is to say that it figures out what is going to happen based in future possible moves. It can work in multiplayer games, so usually done with 2 players, but it can work with more players. It just gets very complicated when it does that. It was originally invented for zero-sum game theory, so it's used quite commonly in game theory. If you've ever done any game theory, I know at the U of C at least, we have 1 or 2 courses in game theory, but I think they're mostly, they might be business or economics courses. It's very similar to the Nash equilibrium. It works on a lot of the same rules that the Nash equilibrium does. Essentially what the Minimax algorithm does is it decides the best move to be made based on possible future moves that are going to be made. And an important thing to understanding how it does this is that it assumes that the opponent, the person you're playing against, is making the optimal move. So it assumes that the opponent is rational, and not only rational, but very good at what it's doing. We're going to see how this works and what this means in a little bit here. So we're going to start off simple. Tic-tac-toe, everyone's favorite game, played for thousands of years. We teach it to children. It helps them develop strategic thinking. You can watch kids play this at younger ages, and you can see them start to develop strategy and then start to figure out how to never lose the game. It's pretty simple. It's 2 players. It's alternating turns, and either a player wins, a player loses, or both players draw. It's also a solved game, we know, because we do computer science. It's pretty straightforward. Computers can play this really easily. If it's played perfectly, you will either win or draw every game. If you're playing it perfectly, you will never lose. And your opponent has to make a mistake in order for you to win. But assuming that both players are making the best moves that they possibly can, then the game will end in a draw every time. And in first year computer science, it's not unusual for you to have to program this and come up with an unbeatable game. So tic-tac-toe is quite simple. So the question here is, what is O's best play in this game right now? This is O's move. They have 1 of 2 choices. Which one is the better move? And it's already been too long. You should be able to see the answer. And it should be easy to see, and it's also quite easy to compute. But let's imagine, let's try computing it, and let's imagine that every state of the board as a node in a tree. So we're going to start out with this board right here. It's O's move, and we're going to imagine it as a state in a tree, and this is going to be called a game tree. So we make our board a node in the game tree, and then we try every possible move that O can make. So we put a branch off of this node, and the first move we try is O moving in the top position over here. And then the next branch we make is O moving in the right position over here. And we can see, based on how this tree is structured, that each edge here is a move by O. Each edge is going to represent a possible move that O can make, and then what the game would look like if O made that move. So I gave the lecture on greedy algorithms earlier this semester, and if we took a greedy approach to this, from what we learned in that, we know that a greedy algorithm is only looking one step ahead. So a greedy algorithm, if you applied it to the problem of tic-tac-toe, would make one move, would look at the games in those places based on those moves, and would try to figure out what the best move is. If you were a greedy algorithm looking at this, though, you would probably decide that that both moves are good. In neither of these games is O winning, and in neither of these games is O losing. So in either case here, nothing really changes, so both moves are equivalent. We know that if you only look one move ahead, that's no good. Both moves are not the same value, so the greedy algorithm is wrong here. This is how a greedy algorithm would work, but we just know that it's bad strategy. Only looking one move in the future is a terrible idea. That's what people who have no strategy do. This is an easy way to win against someone in tic-tac-toe. So a greedy approach isn't really the way to go. But the greedy algorithm isn't... you don't have to toss it out. We just need something that's going to look further into the future. And to do that, we're going to use the Minimax algorithm. So let's look more moves into the future. So we add the next move onto the game, which is going to be X's move. And we can see here that the last move by X would be to put it on the right-hand side here. And in this case, X is going to win the game because X has 3 in a row. Remember, 3 in a row wins at tic-tac-toe. So that's going to represent a win by X. And then if X moves over here, this is going to represent a draw because nobody gets 3 in a row in this game. Easy enough. Very straightforward. Notice that there's no more moves in the game. These games are complete. No one else can move. So these are going to be leaves in the tree. So they're going to be the bottom nodes from the tree. So that every leaf in the tree is going to be an end game. And each edge is going to be a move. So the depth of the tree, how many states we go down, how many nodes we go down, the depth is going to represent how many moves into the future that we're looking. And if you only look one move ahead, it doesn't matter what move O makes, but we know that if you look a little further ahead, it really does matter. So the next thing we're going to do is assign values to each of the end games. So we're going to have some way to measure the game in the end. And we're going to do it quite simply. We're just going to assign a value of 1 when X wins, a value of -1 when O wins, and a value of 0 for a draw. So in this case, X is going to get a value of 1. X wins a value of 1. On the right side, it's a draw, so that gets a value of 0. So we assign a value to those end games, what the final value of the game is if we got to that position. Let's assign those to the tree, so we move them over. And then we want to move these values up the tree to see what the possible outcomes are. So right now we move these values up. And now, from the start state up here, we look down at the possible moves and we see what their outcomes are based on the value. We said that in this state up here, from where we're starting, our current state, O is supposed to be moving. O wants to get a -1 value in the final game, because that's going to represent O winning. So O wants the smallest value possible. A draw is going to be better than an X win for O, so O goes for the lowest value. So it goes this way. It knows now that this is going to be the best move to make. And that's the way that the Minimax algorithm makes determinations on how to play games. Yeah, so O is going to take this branch and it's going to minimize the value for the outcome when it does this. So let's look at a slightly bigger example. Here's a board with 3 more moves to make. X, I believe in this one. Yeah, X is the next one to move. So here's 3 possible moves for X to make. Next branch, these are all the possible moves that O can make from these states. And then these are all the possible moves that X can make based on these states in the board. So we know we've got a bigger game tree here. We assign values at the bottom. Here X is winning, X wins here, and X wins over here and over here. A lot of wins for X. So then we start again moving the values up the tree. Since there's only one value in each of these branches, the value just gets moved up. X has no choice but to make these moves. So these values get moved up. And now it's important to realize that this is going to be O's move. In this, these edges represents O's move. Remember that O wants the smallest value possible. So now O gets a choice of 2 possible moves in each one of these branches on the tree. So O is always going to choose the smaller value. So if we look here, O chooses 0 in this branch, so it moves 0 up here. It chooses 0 on this branch, so it moves 0 up here. And in this case, it doesn't matter. They're both 1, so O just picks one and moves it up. Now X, this is X's move. X chooses the maximum value, and it sees if it goes down this branch over here, it's going to end up with a 1 as the highest possible value. So it goes this way, because it knows now it'll win the game if it makes this move eventually, no matter what happens. So that's the basics of how we would evaluate games and make decisions on what the best values are. So understanding that, we can start asking some bigger questions, like how big is a tree for a full game of tic-tac-toe? Can we generate the full tree? What about other games? How does it work with other games? What's the algorithm that actually does this? And the important part, the one that we really care about, what's the time complexity of that algorithm? Well, let's start out with the full game tree. Tic-tac-toe is a very simple game, but as you can see here, the game tree gets really big really quickly. On the first move, X is always the first to move in tic-tac-toe. X has 9 possible moves. So there's 9 branches off of the start state. Here they all are here. The next move for O, each one of these states, O has 8 possible moves. So from each node on this tree at this level here, there are 8 branches that happen. From there are 7 possible moves for X after that on each one of these. And you can see that this is going to get really big really fast. It's pretty easy to look and see that the number of possible moves is just going to be 9 times 8 times 7 times 6 all the way down to 1, or 9 factorial. That means that there are 362,880 possible game states in tic-tac-toe. If we built the whole tree, that would be the total number of nodes that would be on the tree. But this number is a little deceiving because not all of those are actually valid games of tic-tac-toe. You might be able to imagine that in one of those games, X is able to get 3 in a row pretty quickly, and then the game would end. You wouldn't keep moving, but in that tree, all of those game states represent games where someone gets 3 in a row, but both players keep moving. Because that's every possible game that could be played to fill up the tree. We know that in these games, though, you can finish before that. The game can end. So those aren't all actual valid games. And it's easy to actually compute how many valid games there are. You just have to tell the computer the rules of tic-tac-toe and what an endgame looks like. And when it reaches that endgame, just stop playing the game. And it turns out that if you do that, there's 131,184 games that are won by the first player, X, 77,904 games won by the second player, O, and 46,080 games that end in a draw. Gives us a total of 255,168 total unique valid games of tic-tac-toe. As you can see, this number is quite a bit smaller than this number up here. And just because we like numbers and we're curious, this is the number of outcomes in which players win in 5 moves, 6 moves, 7, 8, 9, the total number of draws, and the percentage of the time that the game finishes that way. So that's interesting. That's tic-tac-toe. What about a bigger game, a game like chess? Anyone that is interested in computers and games will know that chess is a very complex game. About 20 years ago, a little more than that, computers started beating humans, the best humans at chess, on a more and more regular basis. And we know that chess is really complex to calculate. This right here shows, what is this, 18 of the opening moves in chess. I believe there's actually 2 missing here. There's 2 that should be, there's 2 more. So if this was a game tree, there would be 20 possible opening moves for the white player. And from every one of those, there are a lot of possible moves. As you can see, this game tree would get bigger and bigger very, very quickly. And this is what makes chess such a complex game. to try to compute strategies and AI for a computer. It gets really complicated. Even more complicated is a game like Go. It's been calculated that the number of possible board configurations is higher than the number of atoms in the universe. You don't have to know how many atoms there are in the universe to know that that's a pretty big number. And when it comes to calculating things and computing things, that's not a good number. That's really tricky to deal with. And so how big they get is going to be dependent on two basic things. One is called the branching factor, which is how many children each node has. And sometimes this is going to have to be averaged. Like we saw in tic-tac-toe, the number of branches decreases after every move. So for tic-tac-toe, we can average it out and say that there are 5 moves, on average 5 moves in tic-tac-toe. And it's going to depend also on the depth of the tree. So the depth, remember, is how many moves down the tree we need to consider. And in this case, it's just 1. But we saw before, there are trees that get more and more complicated and branch out more and more. So the more branches and the further down we go, the more turns ahead we go into the future, changes things around for us. The time complexity for this is going to be big O of b to the d, remember the branching factor to the depth. And the space complexity is big O of bd. It just has to remember b times d number of states at the bottom of the tree. But we can see, based on what we know of algorithms, that this is not good. This is a pretty ugly number. B to the power of d is going to get very big very fast. And from that, we can also see that what's really going to muck us up is how many turns in advance we look. The depth is going to be really important because that's a power there. So if we look at chess, chess has an average branching factor of about 35. So there are about 35 moves at any one time, possible moves at any one time in chess. If we wanted to look 10 moves in advance in chess, which would be a pretty good number to look ahead if we want to be really strategic, this is the possible number of game states that we would have to look at. And that number is huge. This number is a really big problem for us. This starts to cost us something in computing. So when each node is a game state, remember, you also have to calculate those moves. This isn't just building a tree with this many nodes in it. You have to calculate things for each of those nodes. You have to assign them a value. You have to build a tree to represent them. This has a real cost. And remember that you're playing a game. This is all to play a game. And in a game, you have a finite amount of time to play. A computer doesn't have enough time to calculate all of these positions in the time it has to play. In chess, you've got about 10 minutes to play all of your moves. If you've got a computer that can make this calculation in 10 minutes, you're doing pretty well. If it has to make this calculation every time it wants to move, it's going to be a big problem. But we can cut down on the time by lowering the depth that we check. So if we lower the number of moves we look into the future, then this number starts to go down and becomes more manageable. The problem is that's not a very good AI. That's not a very good computer to play against. If it's not looking further into the future, it's not going to be playing as well because it's not going to know what the possible outcomes are. So we want to cut down on that time. We can do it by lowering the number of turns, but that's not as strategic. Yes, branching factor and the depth of the tree. So this brings us to the Minimax algorithm. So we're going to talk about how it works and some of the things that it needs. So it's going to start at some root, which is going to be some current game state. It's going to use a depth-first search, which we've talked about before in the club. It's going to find all states for a given depth. So for a certain number of moves, it's going to look at all possible outcomes for that number of moves. And it's going to decide based on which player, whose turn it is currently. And it'll start looking ahead at what each player's move is going to be and decide what to do. For anyone that needs a little refresher on what depth first search is, here's a little animation that shows you. Notice on the DFS, it's going to the bottom of the tree all the way down to the leaves on each one of these searches, whereas a breadth first search goes row by row down the tree, examining all the children of a node and going across. So we're going to do depth first search, which is we're going to try all of the moves that lead to an outcome or a final game. Then we're going to go back, we're going to try all the moves that go down this way. So the pseudocode for our min-max algorithm is going to look like this. For each move that the computer can make, or for each possible move, we're going to do a depth first search to some depth or a terminal state. I say terminal state, and that's going to mean an end game. So like in tic-tac-toe, when the board is filled in. We're going to evaluate each terminal state. We're going to propagate min-max values upwards, and we're going to choose the maximum value if it's the maximizing player's move, or the minimum value if it's the minimizing player's move. And then we're going to choose the move with the desired min-max outcome from the root, from the current state of the game. To do this, the min-max algorithm needs a few things. So it needs some way of knowing all the possible moves, which is to say that it needs to know how to play the game. If it's a game like chess, it needs to be able to look at the board and figure out what every possible piece can do, and then try all of those moves. It needs to know what a winning game looks like. So essentially, it needs to know when to stop playing. It needs a function also to evaluate a game state. So in tic-tac-toe, we just assigned it 1 and -1 and a 0 for a draw. In a game like chess, though, you might not be able to look all the way to the end game. As we saw, that's really, really costly. So it needs to be able to look, say, 2 or 3 moves ahead, and then it needs to make a calculation based on what the board looks like and decide how much that board is worth. So if it moves to that point, it needs to assign some value, and then it moves the values up to look what the best valued state is. So it needs some way of evaluating or assigning a number to what a game looks like. It also needs the current game state. You need to know what the board looks like right now. And it needs to know which player's turn it is. Finally, it wants to know how many turns ahead we want to look. Ideally, we would just look to the end of the game every time, but as we saw, there's some games that are too complex to do that in. So the algorithm looks like this. This is going to be min-max. It takes in as arguments some state, so some configuration of the board, what it looks like now, some depth, so how many moves ahead we want to look, and the current player's turn. This is a recursive algorithm, remember, so we're going to start out with some sort of base state. So we're going to say if the depth is 0, which is if we don't want to look any more moves ahead, or if the game is finished, we're going to return some evaluation of the state of the board. If the game isn't over, or if we want to keep looking further advance for turns, we say that if you're the maximizing player, so if you're one of the 2 players, the maximizing player, set a variable called value to -infinity, and then for each possible move, so this is for all the possible moves that are available, we're going to assign value to be the maximum of either the current value, which starts at -infinity, or, and this is where we recurse, we call min-max again, we give it a possible move, so we pass it a board with a move that's been made. We subtract 1 from the depth, so we say that's 1 move in the future, and then we say that the player that's going to move next is the minimizing player. So that's where the recursion happens. And then it returns whatever the value is here. The else statement here is just pretty much the reverse. It's going to be the minimizing player's turn. So this is if the maximizing player moves. This is if the minimizing player moves. Remember, this is just going to be X and O. So these are in tic-tac-toe, these would be the 2 players moving. If you're the minimizing player, the value is infinity, and we want to take the minimum value here, and we call it with the maximizing player going next. So that's the basics of the min-max algorithm. Let's look and see what it actually does when it plays out. So this is going to be a tree. Let's imagine this as a game. With tic-tac-toe, we had these as boards. Let's imagine that these are boards, but we're just going to move values up and down. This is going to be an up arrow for the maximizing player. These are down arrows for the minimizing player. And this is the maximizing player again. This could be any game, essentially. So our algorithm is going to start by going down the tree. Remember, it does a depth first search, so it goes down all the way to some end state. And these are going to be the end states here. This could show us, this could be the game finishing, or this could just be 3 moves in the future, and we don't want to check anything past 3 moves. So let's imagine we go down this tree. We start out, we get the board or the game to this position, we evaluate it, and it says the value of this game is a 4. So it looks at this one, and it says this one's a 6. The maximizing player here looks at both of these and says, I want the highest value, I'm going to choose 6. So 6 gets moved up. There's no more moves for it to check, so it returns 6 up here. This one then goes down. It says my possible values here are 7 and 9. I want the highest one. I'm going to choose 9. This one looks at its options now and says I have the value 6 and the value 9, but I'm the minimizing player. I want the smaller value. So this one is going to choose 6. So 6 gets passed up. 6 gets passed up, no more children, passes it back up here, and this one goes down the tree, does the same thing, picks the higher one, looks again, picks the higher one. This one picks the lowest value, so it goes with 1. Speed this up a little bit. 8 gets chosen there, and 9 and 2. 9 gets chosen here. Minimizing player looks at these, wants 8, and then these 3 values are going to be passed up here. Remember, this is the maximizing player's turn, so they want the highest value of its options. It's going to go with 8. So in this search, in this game tree, we're going to go down this way, and this way. This is going to be the final game state we end up in. And this can be made faster. If you were noticing, you might have noticed at times that there were points where we didn't really need to look down the tree because we already knew that whatever we were doing was never going to be chosen. And this is where alpha-beta pruning comes in. So alpha-beta pruning is not terribly intuitive. I can't show it to you, and I don't think I can show it to you, and you'll just understand what it says, but it's easy to see with an example. So we're going to check if a branch will ever be taken, and that's essentially what alpha-beta pruning does. If the branch will never be taken, we prune it off the tree. That is, we cut it off. So this is what the Minimax algorithm looked like, again, just to remind you. And then alpha-beta pruning looks like this. It's just a little more complicated. What we've done is we've added 2 parameters to the call. They're alpha and beta. So those also get added to the recursive calls for each of the players. Then we've added a check for each player. So after the value is computed for a move, we then compute alpha, and alpha is going to be the maximum of either alpha or the value. And if alpha is greater than or equal to beta, then we break. So this represents going down a branch that will never be taken, and we break out of it. Similarly, same thing for the minimizing player. Beta is the minimum of beta in value, and if beta is less than or equal to alpha, then we break. So let's look at that same example again and take a look at how this works. So we have to initialize alpha and beta for each one of these calls. Initially, alpha is going to be set to -infinity and beta to +infinity. This is our maximizing player. We know that their value here gets set to -infinity. So now we start making our recursive calls. We go down to some game state, and we reach 4. So the value is going to be now passed back up 4, and we know that it's going to be the maximum of the current value, which is -infinity, or 4. 4 is greater than -infinity, so value becomes 4. Alpha becomes maximum of alpha and value. Remember, alpha was -infinity as well, so both of those get changed to 4. We then check, is alpha greater than or equal to beta? It is not. Beta is infinity. Our current value is 4. So we go down the next branch of the tree. We get a 6. We get that passed back up. Value is going to be set to 6 because 6 is greater than 4. And then alpha is going to be set to 6 as well. Oop, that should be a 6 right here, not a 4. So this gets passed back up to... we now check, is alpha greater than or equal to beta? It is not. Beta is still infinity. So we go back up the tree. Remember here, this is the minimizing player, so the code would be at this point right now. Value is the minimum of value and whatever gets returned. So 6 is less than value, so value becomes 6. Beta is then set to the minimum of infinity and 6, which is going to be 6. And we check if beta is less than or equal to alpha. 6 is not less than infinity, so we go back down the tree. So now we start going this way. 7 gets passed up. Notice that now when we go down this tree, beta is set to 6. This is going to be important. 6 is, this beta, 6, basically represents what's the value of the other branch in this tree. The lowest possible branch in this tree. So 7 gets passed up. Alpha becomes 7. And now, very importantly, we compare alpha and beta again. So if alpha is greater than or equal to beta, break. We can see that alpha is 7, beta is 6. Alpha is greater, so we're going to break now. And this is what this represents. Essentially, we're not going to check this other game state. And why aren't we going to check that? Well, it could be anything. We don't know what it is, but we know that this is the maximizing player's turn. And whatever the maximum player is going to choose is going to be the highest number. And right now, the only number we know is 7. So it's either going to choose 7 or it's going to choose what's on this branch. The only way it chooses this is if it's bigger than 7. So we can just assume that if this number is going to be chosen, it has to be bigger than 7. If that's the case, then the number that's going to be chosen here is going to be 7 or greater. And if it's going to be 7 or greater, we know that the other choice is 6. So then we know that this branch is never going to be chosen if the other option is 6. If this is going to be 7 or something bigger than 7, the minimizing player is never going to choose it, so we're never going to come down here, which means that we don't have to check this. So we can break now and go back up the tree. So 6 gets passed up, beta gets set to 6, and we return 6 up here. So this value gets set to 6, and now we run down the tree this way. And this might be a little bit tedious, but we're going to hit another example of a prune in a second. So these values get passed down, 1 and 2. This value gets set to 2 because we want the maximum value. This 2 then gets passed up here. This value is going to be set to 2 because we want the minimum value in this case. And then beta is going to be set to the minimum of infinity and 2, which is 2. And then again, we check, is beta less than or equal to alpha? And it is. Beta is 2, alpha is 6. So we're going to break here. We're not going to go down this tree. The reason we're not going to go down this tree, is that this current player, the minimizing player, wants the smallest value. The choices are currently 2 and something else. This player would have chosen at least 2 or greater, and we're not going to choose that. We know we're not going to choose that as the maximizing player, so we're going to go with whatever this value is over here. We're going to go with the 2. That means we don't have to check these branches. So we pass 2 up, and now we go down this end of the tree as well. We choose 8 and 1. Those values are going to get passed up, and beta is going to get set to 8. And is alpha less than beta? It is not. So we pass this back down. We get a 9 here. We change our values around. We do our alpha beta check again, and alpha is greater than beta this time, so we're not going to examine that branch. Now we get 9. We look. The 8 is going to get passed up. This move over here chooses its maximum value of all of these things. It chooses 8. And now it's going to go down this branch on the tree. And as we have seen, it is going to return 8 as the highest possible value. So 8 is going to be the best move here. And if we take a look at our tree, we're going to notice that we didn't evaluate 1, 2, 3, 4 of the possible states. This is of 12 possibilities. We cut 4 of them off. Which means that's about 33% fewer calculations that we had to make for moves and board states to figure out our eventual answer. We come to the same thing, but we don't have to do as much computation. And this is really good for us. Remember, this is what Minimax looked like, and then it looks like this with alpha beta. So we cut a bunch of stuff off. And this is good. This makes things a lot better for us. How much better does it make it? Well, the time complexity of Minimax was big O of b to the d. Exponentials are really bad. We don't like them. But in alpha beta, the worst case is still going to be big O of b to the d. Why is it the worst case for alpha beta? Well, in some cases, you're not going to be able to prune any branches off the tree. It's possible that the numbers are arranged in such a way that you never get to cut anything off. In the best case, it's going to be big O of square root b to the d, and that number is much, much better. We got a square root in there that cuts things down quite a bit. And there are ways to organize those numbers in the tree to make sure that we get closer to the best case, so that we move the number from worst case, we move it closer and closer towards the best case scenario. So in a game like chess, one way of doing that is to try moving all of the pawns first. In a game of chess, if you can capture something with a pawn, that's usually a good move. If it's another pawn, then that's okay. But if you capture a piece that isn't a pawn, that's a really good trade. You always want to be capturing things with pawns. So if you capture like a rook, a bishop, or a knight, that's a great move. And if you do that, it's unlikely that there's going to be better moves. So that means you could prune the other moves off the tree. So there are strategies in games to move it from worst case closer and closer to the best case. But it's never exact. It's always choosing tweaks on your algorithm to get it closer. So that's the essentials of alpha beta pruning. So we're finished for that. The competition should be live. I won't be going over any of the solutions for this week's competition. Just one moment. Let me pull it up here. But there are 3 problems this week that can be solved with alpha beta pruning. Just one second. Yeah. There are 3 problems this week that can be solved with alpha beta pruning. If it ever wants to load the contest for us. Here we are. Yeah. So there's a few problems here. I believe Millionaire Madness is the first one. It's 2.5 difficulty. So it's not too bad. You've got a lot of time and a lot of memory to do it with. It can be solved with a Minimax algorithm. There are also other ways to solve it. A little hint, you don't have to use Minimax. You could use Dijkstra's algorithm to solve this one. But that's another way to do the same thing. Millionaire Madness, I believe Peg Solitaire is the next one. This was, I think, a 3.5, and this is actually going to be a game. So this describes a game with pegs that are able to move around. So you can use Minimax to solve that. And finally, Muddy Hike is a 4.2 difficulty problem. It comes from Mount Allison from a recent contest of theirs in 2017. So yeah, those are the problems. That's the competition for this week. If you have any questions, by all means, go ahead and ask in the club Discord server. Otherwise, we'll see you guys hopefully next week. Good luck with the last week of classes this week. I know it's been a really long semester for everyone, but you're almost there. We're almost through it. It'll all be over class-wise in just another week. Then we hit exams. We'll be hanging out again, remember, next week, doing some fun word problems, casual problems. It'll be more geared towards a bit of a hangout to try to decompress as we go into exams. Hope to see you guys there, and thanks for playing along. Good luck on the contest this week. Have a great week, everyone.